All right. Getting on to the end of the show. How's the conference been? Been having a good time? Yeah, I love this place. And I mean, it's a little warm for Denmark, but I'm from Vancouver, and if it gets this nice, you go outside. Like that's because it doesn't happen very often. We got lots of rain and clouds, but we don't get lots of hot, sunny days. My name's Richard Campbell. I make a bunch of podcasts. I think a few folks know that. .NET Rocks. Run as radio for a while. They're the tablet show. Although I haven't been mentioning it, I should also that I work on Windows Weekly, which is a show I do with Paul Thurrott and Leo Laporte, because I was just not making enough podcasts. But this is really about the geek out. So these come from .NET Rocks, and I've done about 100 of them. I do a couple every year now. And they were just sort of fun passion projects for me. We were making enough shows that I thought I could do something silly each month, and so we talked about energy and space and a bunch of other technologies, and they've been very popular in their own right. But this talk comes about because I did the Moonbase podcast. So I did a talk about building bases on the moon based on a European Space Agency paper, and the podcast did well, as the Geek Outs usually do, but then I got a call from NASA, which is weird. I got an email. And I didn't believe it at first. Like, would you? But no, it turned out it was actually NASA. And they're like, hey, we really like the way you talk about the moon. I'm like, oh, thanks. That's cool. It's like, would you ever consider doing a presentation about building bases on the moon? I'm like, yeah, okay. And it's like, do you know about PowerPoint? Because we like PowerPoint at NASA. I'm like, yeah, Chuck, I know about PowerPoint. And he only knows if he's a podcaster. He doesn't know. So he says, well, we'd really like it if you'd come talk to us about the moon. I'm like, okay, well, talk to who? Well, us. NASA? Yeah. It's your stuff. Yeah. You want me to talk to you about your stuff? Yeah. Okay. So, in the fall of 2017, I got to go to the NASA Ames Research Center. And in the end, this is the big entry board on the way into the facility. And there's my name. And I talked to a bunch of NASA folks about building bases on the moon, and that was weird, but a lot of fun. And then the conference community found out that I'd done this talk. They're like, well, will you do it at the conference? And I'm like, okay. So since then, for a few years now, I've been doing sort of space-related talks in one form or another. This is sort of the latest incarnation of this. Usually I stick pretty hard to just the current science, like where are we right now, what's happening, what's working, what's real, what isn't. There's a lot of speculation in space technology, and science fiction doesn't make it any easier. But this particular talk is a little more speculative. It asks that question, how could we become a spacefaring civilization? And what I mean when I say spacefaring is that people routinely work and live in space. I'm not saying they never go back to a planetary body, but right now we're purely expeditioning, right? I mean, they literally call those folks on the space station an expedition, typically for no more than 6 months. There's occasional exceptions to that, and then they go back. But what if there was routine work up there? And then, of course, that begs the question, should we even bother? And there are good cases for us to get better at space than we are right now. At the moment, it's just kind of an exploration thing, and we've learned some interesting stuff. But arguably, there are key things we could get better at. I would mention, first and foremost, the dinosaurs died out because they did not have a space program. And we have an opportunity to not be like them. We could do something about it. In fact, we've been working on this problem. There is a whole group at NASA called Planetary Defense. And one of their initiatives, and it's not the only one, we can talk about some of the stranger ones, but that one of them is this issue around large objects colliding with the Earth and doing serious harm to it. And we're now at a point in our civilization where we're beginning to test dealing with asteroids. So a couple of years ago, the dual asteroid redirect mission was actually accomplished. They sent up a small satellite, about 500 kilograms, and they flew it towards a binary asteroid system. This is the two asteroids. So the bigger one there is Didymos, which is about 780 meters across. That's a pretty good sized rock. And the little one beside it, it's actually orbiting it. It's called Dimorphos, but we generally called it, Little Diddy. And so this is actually photos of the spacecraft, from the spacecraft approaching the smaller moon. It is coming at it at about 6.6 kilometers per second. So moving. We're getting close now. And that frame didn't finish. Guess why? Actually, they did an even cleverer thing. The Italians had a pair of microsats that were released from the orbit, from the spacecraft about a week before, and they had cameras on them to film the impact, and then they flew past. And so that flash you're actually seeing is the impact of that of the spacecraft into Dimorphos. Now, at the time, they were hoping the orbit of Dimorphos was about 11 hours to go all the way around this asteroid. And they picked it because it flies close enough to the Earth that we could map it, we could really see what it was doing. And they were hoping to change its orbit, reduce the orbit by about a minute. If they could reduce like 70 seconds, that would be a win. They actually reduced the orbit by a half an hour, which is confusing. Like, why is our math wrong? We've estimated the masses. Like, what's happened here? And one of the biggest issues we've come to appreciate is that a lot of these asteroids are rubble piles. They're not a solid rock. They're a conglomerate of smaller pieces. And so when the impactor struck Dimorphos, it created this titanic spray. They're talking thousands of tons of rock came flying off of that. And that impact sequence actually changed the orbit more. But it also formed a tail, almost 30,000 kilometers long, of rocks sprayed out behind Dimorphos. There's another mission headed there to now take a look at the post-impact and try to map things out again to learn a bit more. So it speaks to us making progress on the idea that we could actually divert an object away from colliding with the Earth. Asteroid mining, of course, very popular in science fiction. It also could become science fact. We've played with a bunch of the technology around this, and there's the strong argument here. There's a really interesting NASA paper that talked about the idea that we may be in a very small, maybe 50-year window where key resources, rare earth minerals and things that we need for spaceflight are plentiful and inexpensive. And that over the next few decades, because we use them for other things, they're going to become more expensive to the point where it might be prohibitive to actually mature a space program anymore. And so, we're on a time limit, right? That sun's been up there for 4 billion years. We probably got 2 or 3 more billion before it starts to swell and incinerates everything and really messes with your sunscreen. And so in that time span, we've got to think beyond that. Well, now there's an argument that we have a resourcing problem that's going to only be sustained for so long, and if we can get to start extracting those resources from the rest of the solar system, that lifts that limit entirely. But it's got to be now. Realistically, that in the next few decades, likely most of us will see the progress towards being able to extract these resources. Another big reason to have a space program is that we do have adventurers in our society. They're weird, but we like them. They can be inspirational. They push the envelope all the time, and if you don't give them something to do, they find something to do. So give them something to do. I think it's also useful for civilization to have an aspirational mark, to be something out on the edge, past where any of us are comfortable. I've done a few of these talks where I've talked about regular people going to space and just how sick they get. Like normal astronauts are a strange bunch. The kind of person that would be able to get 3 PhDs and then also want to routinely endanger their life, that's odd. One of my favorite stories is a NASA astronauts that did most of their construction of the International Space Station found that they were having problems with their fingers because the gloves are pressurized, they're about 3 psi, and so it's fairly tough to grab things when you have to press against your glove, to the point where they would bloody their fingertips. Their nails would bend back. And so 6 of them had their fingernails surgically removed so that they could do these roughly maybe 40, 100 hours of their entire lives involved in doing spacewalks to build the space station. They want to do it better. That's the mind that makes an astronaut. We should give those people things to do. So, from a society's point of view, we have all these different pieces about protecting ourselves, about actually being able to stretch to limits. Let's talk about how we're doing. All right, and I'll use Robert Heinlein's quote here that once you get to Earth orbit, you're halfway to anywhere in the solar system. Getting out of the gravity well that is the Earth is a substantial effort. It's the vast majority of the work that we do these days, but it has improved substantially over the past few years. Now, in science fiction, including folks like Robert Heinlein, we've talked about things like space elevators being the cheap, if we could build one, that would be the cheapest way to get to space. So this is the idea of a tether. It's not actually built up from the ground. You can't hold anything up like that. What you do is you would capture an asteroid and you would position it about roughly geostationary orbit, maybe a touch higher depending on the balancing, and then you would build a cable out from both directions. One is the counterbalance, and the other side would go down until it touched the surface of the Earth. And now you have a cable essentially stretching through the atmosphere up to this balance point, so it spins with the Earth in geostationary synchronization. Very cool idea, works great in comic books. Few problems. One is material strength. It is incredibly hard to have a material strength strong enough to take the stresses that we're talking about here. Now, we have in the lab made small quantities of extremely strong materials, diamond nanotubes and that sort of thing, that we've built almost millimeters of, that seem to test to the strength level that would be necessary to build something like this. We just now have to make hundreds of thousands of kilometers of it perfectly and assemble it into this scene. And even then, there's more problems. This is a really long elevator. You get bored going up 30 floors. Try 60,000 kilometers. How fast does that thing have to go? And speed actually matters, because one of the side effects of going through from the equator up to orbit is you're going to go through the thickest, densest, and largest parts of the Van Allen belts. These are high concentrations of radiation formed by our Earth's magnetic field to protect us. And now you're going to slam astronauts through that. Now, in the Apollo missions, they went through it, but they cheated. They took a very circumspect orbit far to the north, so they avoided most of the Van Allen belts in the first place, and they were moving fast, so they were only in it for a few minutes. On an elevator, you'd be in it for hours, potentially days. So it's almost impractical for us to ever consider one of these, except perhaps for cargo. But considering advancements in rocketry lately, and I don't know that we need it anymore. SpaceX is pretty close to making a fully reusable rocket. The Starship is getting ready for its 5th test flight, and it is absolutely massive. That's a 9-meter in diameter rocket, and 300-something meters tall. The lower stage is supposed to be fully reusable. They haven't done it yet, but they've done it with Falcon 9. They're really trying with the super booster that it will spend 2.5 minutes pushing the Starship up, and then it will turn around, fly back, and land on the platform, which is insane. And then the upper stage will go the rest of the way to orbit, do its mission, and then deorbit and land on its tail like Buck Rogers. And we've seen a bunch of these tests if you've been following along. This is ITF-4, the last mission. A few things I really appreciate about this. One of them is, notice that even after all this work, they still had an engine out on launch. Not that it affected the mission, it worked just fine. They were able to have a proper separation. The actual mission diagram looks more or less like this. So after about 2.5 minutes, they had a hot stage. The upper stage continued on to orbit. The lower stage did a boost back burn, so it decelerated itself, and then it descended towards the ocean. It landed close enough to its intended target that a camera they had mounted on a buoy and pointed in a direction caught the entire landing. So that part worked pretty well, but they have a lot of experience with it. They have 300-plus flights with the Falcon 9 doing this sort of stuff. The upper stage had a bit more drama as it actually did get to orbit, but we've never had a vehicle this large have to re-enter before. We've really never had a vehicle this large before. 9 meters into orbit is unprecedented. A few things that were cool about this re-entry. The first is it's so large that it's not entirely encapsulated in plasma on its way through re-entry, so they had camera feed the entire time. No other spacecraft has ever been big enough to not be completely radio silenced by the plasma ball that's around it as it re-enters. This one had multiple channels of HD TV the whole way. And if you watch this particular one, that flap there, we'll call it the little flap that could, actually experienced a burn through. There was one camera that was on it. It was covered in debris because It was a dramatic re-entry, but the heat got underneath the tiles and blew them off, and the control, we kept expecting it to just lose it and blow to pieces, but it didn't. It made it all the way. They did do a soft landing in the ocean off the western coast of Australia. It destroys the vehicle in the process, but the bottom line is they more or less controlled all the way down, and now they've revised the entire heat shield system to try and have more success for the next flight, which is imminent. And probably in the next month, we'll see Flight 5. So progress is being made. Lots to go, but it's an interesting time. Now, SpaceX has already changed spaceflight dramatically in terms of price. This is the only set of numbers I'm really going to have on this whole deck. I'll start with the Atlas V at the top. That's a rocket from the 1990s. They're making no more. The last few are flying. This is United Launch Alliance's workhorse rocket. 20 years ago, before SpaceX was in the business, it was $25,000 a kilo to low Earth orbit on an Atlas V. Now that Falcon 9 has come along, they were able to get the price down to about $8,000 a kilo. Falcon 9, basically the cheapest ride into space right now. If you have a choice of lift vehicles, you take a Falcon 9. They're very reliable, and they're incredibly inexpensive compared to anything else. The Falcon Heavy is nominally less expensive because it can lift a lot more mass. Not that we ever do that. So while the numbers work that way, it's not how they tend to be used. A Falcon Heavy is literally 3 Falcon 9s strapped together, which is very Kerbal Space Program if you're into that sort of thing. Vulcan is ULA's new rocket. It's the replacement for the Atlas V. It is a more efficient rocket. They have flown it exactly once, and it served fine. And that is the latest update to the rough pricing. So 4,500 a kilo is not bad. It can't catch Falcon 9, but it's actually, a comparable class rocket. New Glenn is Jeff Bezos' rocket. This is Blue Origin. It has never flown, so these are speculative numbers. It's a 7-meter rocket, which is very large. The Falcon 9, for example, is a 3.25 meter wide rocket. And the reason it's 3.25 meters wide is because that way it fit on United States interstate highways. They wanted to build the rocket in California because they got good tax credits, but they had to fly it in Florida. If they made it any bigger, then they had to barge it through the Panama Canal to get it to Florida, but at 3.25 meters, it'll just fit on roads so they can truck it to Florida to reduce costs. And there's a rule with rocketry, you can only be so tall for your width. It's called the fineness ratio. And the Falcon, normally it's about 15 to 1, so you're about 15 times taller than you are wide. The Falcon 9 is now at 18 to 1. It is an extremely long rocket. And it's amazing that it works as well as it did, although it's had a couple of misadventures this year, unusual. So wider rockets lend themselves to much larger payloads because we can stay within the fine ratio and push a lot more. So New Glenn has the possibility to be this incredible heavy lift rocket. 45 metric tons is a lot in a 7-meter rocket. The Space Launch System is NASA's rocket that uses all the old shuttle parts. And so they call this now Artemis, and we'll talk a bit about it a bit more later on. It's pretty much the most expensive way to make a rocket you can imagine, and there's a couple of good reasons for this. NASA is a political entity that ended up originally was NACA. Its job was to establish aerospace in the United States, which it achieved. Then they gave it the space problem during the Cold War, and it focused on that from then on. And one of the things they learned as a political entity is that you get as many states involved in any project you're doing, and you're less likely to have it canceled. And for the 30 years that they ran the space shuttle, they managed to get something for the space shuttle built in every single state in the United States. Now, this has come back to bite NASA. It works the other way, because as the shuttle was finally wound down, all of those congressmen that were involved in every single state said, oh, no, you can't stop. I have a lot of people employed doing that now. And so the Space Launch System is them repurposing all of that technology, even though it's from the 70s, with some upgrades in the 90s, and all of those people to continue to build rockets. It's a very expensive way to fly a rocket. They're estimating $4 to $4.5 billion per flight, and they're only going to fly every few years. And in fact, they've only flown really once. Starship's numbers are completely speculative. Yes, it's a very heavy lift rocket. Depending on who you ask, price per kilo could be $10 up to maybe $1,000. So I kind of lean towards about $100 because in theory, the entire vehicle is reusable. It's like an aircraft. You do some maintenance, you refuel it, you fly it again. And fuel is cheap. So now you're talking about being able to lift a human into space for about the price of a first-class ticket across the Atlantic, right? Maybe $10,000, $20,000. That's a big change, and it opens the door to a lot of possibilities. Our main asset in space these days is the International Space Station. European Space Agency contribute heavily to this, so did Canada, obviously the United States. Russia is a partner. Things are a little strained at the moment. Japan and others. It's been up there since 2000. It is getting very old. It is wearing out. It has done its job. Its principal task was to teach us how humans function in free fall, which is to say, poorly. Free fall is not a normal condition for humans. Humans need gravity. And so it is challenging for us to be comfortable out there. And as we go through this conversation about becoming a spacefaring species, we're going to have to deal with the free fall problem. This station is going to last probably till 2030. The Russians only committed to 2028. It's their parts that are the oldest, so they're the most worn. There's an idea that we ought to lift this into a higher orbit and keep it. It's almost impossible. It's very, very difficult to move a vehicle this large. This thing's the size of a soccer pitch, and it weighs 450 metric tons. And what's happening is that the aluminum structures of the oldest parts are embrittling, and they're starting to crack, and they're leaking, and they need to be replaced. And it's a design, again, largely from the 70s and 80s, updated in the 90s with some improvements. We can build better stations, and in fact, that's exactly what NASA's intending to do. NASA doesn't want to build another space station. What they're doing is they're contracting out station manufacturing. So they're basically providing specifications for what they want from different space stations, that they'll buy time on it, and allowing industry to actually deploy them. And there's a bunch of proposals out there in varying states of development. The one from Jeff Bezos that involves the New Glenn is the largest. It's called Orbital Reef. And so those are all 6-meter wide cylinders as opposed to 3.5-meter wide cylinders that the International Space Station had, because the International Space Station modules had to fit in the space shuttle. So they couldn't be any bigger than that. It sounds like a good idea to have a 6-meter wide cylinder. It's actually not, because when you're in free fall, if you can't touch a wall, you're really stuck. Like, you're just going to spin, right? Like, so when they came up with this size, I said, you need to fill it in. Like, you have to build it into panels and so forth so that people can always touch a wall in free fall, or they really do get trapped. But this is actually 3 of them. So the idea is to have more smaller space stations that can be specialized in different tasks. So some of that's going to be human science, some of that's going to be manufacturing. We do need to experiment with centrifuges, and those aren't compatible with microgravity experiments, so you need to have them in separate structures. So this is one form of it. One of the coolest parts of that whole thing was this little self-contained spacecraft from Genesis Engineering, a single person spacecraft for going around on the station. Instead of having to get into one of these pressure suits, which takes hours, you have to breathe pure oxygen for a few hours to get the nitrogen out of your system because you have to lower pressures. It takes at least one other person, usually 2, to get you into a spacesuit. Like, just to be clear, if you watched Mark Watney on Mars, Mark Watney dies, because he can't get in a spacesuit by himself. There's no way. This is not a thing. So those little pressurized self-contained units would be a much easier way to go and explore where you need to get your eyes on parts of the space station. This is an inflatable made by NanoRacks that's tended. And then this is the one that's the furthest along. This is Axiom Space. These are a bunch of ex-NASA space station folks who formed a company to build their own space station. That center piece there, that's actually, in this mock-up connected to the International Space Station, that is under construction now. Metal has been cut. Their intent is to assemble the station at the International Space Station before 2030, so that they don't have to build all the self-contained stuff you would normally need to build a separate space station. And then once they complete their station, then it'll be separately free-flying. They're far enough along that NASA's discussing whether or not to take a few of the newer modules that are on the International Space Station and keep them with the Axios station. These are also the folks that have been flying tourists to the International Space Station on Crew Dragons. So, again, there's a lot of stuff going on in this space. So, in the next few years, we're going to lose the International Space Station, and we should get a bunch of new ones. I would remind us all that there are actually 2 up there. The Chinese have their own, the Tianxian, which is very much like the old Russian Mir in design, and it has 6 people on it, and they're doing their own science. The Chinese are not as forthcoming with what they're working on. NASA tends to be very public, but they are running big science there. Okay, let's talk a little bit about the moon. This is my favorite picture of the moon, because it's a picture of the far side of the moon, not the dark side of the moon. That's not a thing. That's a song, right? The far side of the moon gets as much light as the front side because things move around. Always, when you see pictures like this, and it's in our world of CGI, when you see a picture like this, you should ask the question, who took this picture? Because this is a tricky picture to take, and it really is a photograph. This is a picture from the Discovery satellite. It is a solar observation satellite, so it sits in the Earth-Sun L1 location, which is a stationary point gravitationally between the Earth and the Sun, about 1.5 million kilometers away from the Earth. Its main job is to study solar weather, to give us some warning when there's major coronal mass ejections. You may have noticed, you guys have certainly seen the amount of aurora borealis we've had this year. So the sun's been very active, and that stuff can get damaging. And so the solar weather satellites are about warning us in advance when something like that's going to happen so we can protect certain technologies. Satellites suffer from it. Power grids have configurations that are more tolerant so that we don't get into really real risk. The Discover satellite was able to take this picture from 1.5 million kilometers away because it has a telescope on the back. Because they know, based on their position, they're always going to have a perfect disk of the Earth. So routinely, they just snap a photograph. Now, actually, they don't snap 1 photograph, they snap 4, because the sensor is monochromatic. But they flip different filters in front of it to build color pictures. And every so often, the moon whizzes through the frame. And that's when you get a picture like this. And one of the proofs that this is a real picture is if you get up real close to that, you'll see on the leading edge of the moon, there's a green haze. And it's because they take the green picture last. And the moon moved. So I'm sure a CGI guy could do that, but why would he? Anyway, let's talk about the moon. Specifically, there's the Apollo missions. This was in the 1960s and the 70s. It was a part of the Cold War between the United States and the Soviet Union. And the Americans were successful in putting 12 men on the moon. 11 of them were test pilots. 1 of them was a scientist. This one, down in the corner. That's Jack Schmitt. Jack Schmitt was a geologist. He helped train all the NASA astronauts on how to do exploration on the moon, which is very challenging to do. They are test pilots. If you ever get a chance to talk to any of these test pilots, and most of them are dead now, and you ask them what were they thinking while they're on the moon, the main thing they were thinking was, please God, don't let me screw up, because that's how test pilots think. But Jack was a geologist, because geologists like rocks. And Jack was the one and only scientist to ever set foot on the moon. There he is right there. You'll notice that Jack is dirty, because Jack liked rocks, and so he got down in the rocks a lot. He fell over a bunch. He also kept flipping up that gold visor. It's the thing that protects his eyes from having the sun burn his retinas out, but it changed the color of the rocks. And Jack likes rocks, so he'd flip the visor up to get a better look at the rocks. If you ever listen to any of the recordings of Apollo 17, you'll hear Capcom casually saying, hey Jack, when you get a sec, could you put your visor down? They leave off the part, dumbass, because he's endangering the mission, right? He's also the only astronaut on the moon ever photographed visible face, because he kept flipping his visor up, and they actually snapped that picture of him. Actually, take a closer look at this picture. You see this? Those are paper cards. So on his left arm, there's cards that literally map out minute to minute what he's supposed to be doing on the moon, right? They only have a few hours on the moon. He had 3 7-hour sessions on the moon, and they were trying to get as much science as possible. So literally everything's mapped out. But as he was finishing the cards, he was ripping them off, sticking them in his visor so he could lift it up to look at the rocks. And Jack found better rocks than anybody else because he's a geologist and he knows what the heck he's doing. And we know that real science is not, eureka, I found it. Real science is, what the hell is that? Like, you have to know enough about rocks to know that's a weird rock. And Jack's the one who found an unshocked piece of olivine, which, if you're into geology, is very cool. But unshocked olivine indicates volcanic activity on the moon. It was proof that there was volcanic activity on the moon. And the one scientist we ever sent to the moon found it with all of the limitations that he had. Imagine what would happen if we had a group of scientists on the moon for weeks. I don't know what we'd learn, but I'd sure like to know about it. Anyway, that's Jack. The real reason the Apollo moon missions ended was this vehicle, the Lunar Excursion Module. It's a very dangerous machine. It is capable of sustaining 2 humans on the moon for about 3 days, raising them, getting them down there and back again. It had a set of failure modes in it that were not recoverable. If the landing gear collapsed, they were dead. If the life support system cranked out, they were dead. It takes more than 3 days to get a rescue party up, so there's just no way to save them. And remember that this was a military mission to prove American superiority over Soviets. So the moment it worked, the politicians wanted to stop. Everything after that is just risk. And so they cut the missions back and cut the missions back. In fact, Jack was supposed to fly on Apollo 18, but when they canceled 18, there was a big hubbub that says, we've got to send at least one scientist. And so they bumped Jack up to Apollo 17, and he did his mission, and that was it. They built enough hardware to fly all the way to Apollo 20, and they used that hardware to build Skylab and to do the Apollo Soyuz missions, where they actually had Russians and American astronauts meeting up in orbit. That's a whole other bigger story. Moon missions are back. It's now called the Artemis Accords. A lot of countries, including the European Union, have signed on to these, and the intent is to return humans to the moon. Why now? Technology has advanced enough now that we believe we can put humans on the moon safely. And this is that paper that I was reading back in 2016 that became that talk in 2017 that I ended up doing for NASA, was the European Space Agency assessment of we can build an Antarctic-like base on the moon, put humans on it for roughly 40 days at a time, and do science. And so Artemis is their approach to doing this while using a rocket that's really just a political football. The Artemis 1 mission has already flown. It was unmanned. It was really a tester for the Orion capsule. The mission was very successful. They did a bunch of things here that they've never been able to do before. Computer technology has advanced so much since the 1960s and 70s that they were able to compute orbital behaviors they thought would work but have never flown, and they flew it on Artemis 1. So they did some gravitational tricks and different ways of orbiting to prove that all of this math they've done is correct. And then they returned the empty vessel back to the Earth successfully. Artemis 2 is supposed to be next. It was originally supposed to fly in 2023. Then it was supposed to fly in 2024. Now they're saying September 2025. It's going to be manned, but it's not going to land on the moon. It's 4 people, 3 Americans, 1 woman, and a Canadian. Are going to go up. They're going to do an Apollo 8 style mission. They're literally going to go around the moon, and they're going to come back. They're proving out the life support systems. They're proving out the operating spaces. They're just figuring out if humans can function under these conditions. But the mission's continues to be delayed. One of the main pacing items is what's going to do Artemis 3, which is to land on the moon. And now you need a lander. In Apollo, they did this approach where they carried the lander and the reentry vehicle together. And that is great for one-and-done kind of missions. But if you really want to make a sustainable mission, you need more reusable parts. If you keep having a lander that leaves its base behind every time you land, your parking lot's going to fill up. And so NASA is big on, we need a fully reusable lander. SpaceX has presented one. It's a modified version of Starship without the reentry shielding, with a set of engines high up on the body for doing the landing so they don't blow big holes in the moon when they try and land. But it is 165 meters tall, right? Sorry, 165 feet tall, 50 meters tall. So better find a flat spot to land. And, I mean, those are the people, right? That's where they are there. This is all fuel tank. This people part starts up here, so you're going to need an elevator too. And watch that first step. That's a long way down. Also, to make it work, you're going to need to refuel it. So they're going to lift it off from the Earth. They're going to get it up to orbit. Then they need to fuel it up enough to fly it to the moon. Then they leave it in orbit around the moon. Then the Artemis rocket flies, the SLS, that carries the Orion capsule with the astronauts in it, flies to the moon, meets the lander, they transfer over, and then the lander goes down to the surface. They do their mission, and it comes back up. They transfer back onto the Orion and return to Earth, which seems a little inefficient. Like, considering it that lander has all the radiation shielding, all the life support, all the food, like, I don't know what we need the Orion capsule for, except for re-entry, right? You have to have something you can get in that can fly you home. Like, one would argue, if we're going to do all these refuelings, why not fly the SpaceX vehicle back to the Earth, meet it with a Crew Dragon, load them up, fly it out to the moon, do its thing, fly back in. You just have to do the refuelings. By the way, when it comes to refuelings, we've never refueled anything in space. We don't really know how. We have to figure that out. There's lots of proposals. All of them look vaguely like HR violations. Here's the problem. Here's the inside of a liquid oxygen tank in a Falcon 9. So we're under acceleration right now. See if you can tell where the acceleration stops. Notice the difference? Fuel doesn't sit at the bottom of the tank as soon as we're not in motion. You have to settle the tank if you want to be able to pump the fluid. You always have to be not only moving, but accelerating to keep the fuel settled. So that side by side would be one approach, and then you have to thrust a little to put the fuel down at the bottom of the tanks, and then you can pump it. There's also an end-to-end. It's another HR violation, but you could accelerate it, move it that way. One of my favorite designs, and this is where we get into what does it mean to become spacefaring, it's infrastructure in space, is build a gas station. So here I have multiple tankers docking to a structure. When I need to pump fuel, I rotate the structure. That settles the fuel, allows you to pump. You don't have to change orbits. You're not moving around near as much. And I could actually have several of them fully fueled so that when I want to fly something that needs to go further, it just arrives at the gas station, fuels up, and goes. Plus, once I have a gas station, I now have a market. I don't have to supply my own fuel. I can just offer a price. I will buy liquid methane at this much per ton and liquid oxygen at this much per ton. Where you get it from, that's up to you. You want to fly your own rocket off the Earth, that's fine. You want to extract it from asteroids and bring it here, fine. You want to get it from the moon, fine. So have a gas station at Earth, you probably want one at the moon as well. That way we can stage more fuel in place. This is not a totally weird new idea. They've been talking about building fueling stations. This is a design from 2011 based on an Atlas V for storing liquid oxygen and liquid hydrogen. Never got built, but it is something that's been discussed for a long time, is how do you keep fuel in orbit so that you have more of it when you need it. Now, once you get on the surface and you deal with your elevators and so forth, what are you going to do? Well, we've got to learn to work on the moon again. Right? We built suits back then that were designed to work on the moon. These are different now. I've used this picture before, but I wanted to talk a little bit more about it. This is actually a mock-up from Blue Origin. This is a non-reusable lander, so that base piece stays behind. That's the ascent stage that goes up. Again, that's problematic if you actually want to build a base, because you're going to end up with a bunch of those. Actually, the most interesting thing in this picture, if you're into space, is the fact that this astronaut is kneeling. Something the Apollo astronauts could not do, because their suits were inflated to keep them healthy, and that basically meant you couldn't bend your knees. And if you watch them walking on the moon, they kind of Michelin man it. They're like this, because bending your knees is really hard. So the implication here is that we've solved that problem. We've done it without having large amount of volume around the legs. It's tightly compressed, so they can articulate their joints and move a little easier. NASA also wants an EVA suit that'll function on the moon for 800 hours. The current record is 22. The environment on the moon is very hostile to pretty much everything. It's not only a high radiation area and extreme, 250 degrees centigrade in the sunshine and negative 200 in the shade, but the regolith on the surface of the moon has never had any erosion done to it, so it's very sharp and abrasive. And it does damage to the surface of the suit. It does damage to any moving parts. And it sticks to everything. And so one of the challenges, can we build a suit that we can actually get that dust off of it? One approach would be, don't bother, keep the suit outside. So that backpack actually backs into an airlock that locks in place. And then it's open from the inside, and the person pulls himself out of the suit. So the suit stays outside all the time and doesn't contaminate the inside of the station. Another approach is they've been playing with this thing called Spider, because they love names. The Spacesuit Integrated Carbon Nanotube Dust Ejection and Removal System, SPIDER. Really what it is an electromagnetic field built into wires in the suit that electromagnetically pushes the dust back off, which would probably be cool to look at. It's like you'd sort of stand there and then pulse it, and all the dust would fall and slowly fall down off of you, but we'll see if it works. Current proposal for the base is around the South Pole. This was a design from Blue Origin of a landing zone for different landing sites, because remember, they wanted to leave their bottoms behind. Resource storage. The reason for the South Pole is that there's a huge crater there, the Shackleton crater, that's continuously shaded. The sunshine never lands there, so there's a lot of ice in it. But the rims are really high, and so they almost always have sunlight. Here's an animation of the Shackleton crater. And again, you should ask the question, who took this picture? This is an entire year of the moon looking down on Shackleton crater. This is a composite image built by the Lunar Reconnaissance Orbiter. Every time it flew over Shackleton crater, it would take a picture, and they assembled them together over time to give us an entire look at what Shackleton would be like. About 15 Copenhagens would fit inside that crater. It's big. And so the rim has light continuously, so you can put your solar arrays up, and then you can drive down into the dark to extract water ice, and that becomes fuel. One of the European proposals is for better navigation. I mean, the moon's gravity is fairly irregular, plus or minus 2% in spots. It messes with deorbiting and landing, depending on your approaches. You'll remember the famous story in Apollo 11 of how Neil Armstrong at the last second had to take manual control of the lunar lander, fly it past a bunch of house-sized boulders, and find a new landing site with 20 seconds of fuel left, like it was supposed to be made for TV, like Kubrick wrote that script. What actually happened, and if you listen to the whole, the entire audio of the landing, which is about a half an hour long, they separate from Columbia. Eagle separates from Columbia on the far side of the moon to land on the near side. And they had mapped out the path that they were going to fly over exactly. They knew all the landmarks. And so they're timing how often they're passing these landmarks to know that they're on time. And within 5 minutes, Neil says, "We're long," which means he's passing the marks too soon. They'd passed over a dense part of the moon, and it accelerated the vehicle and moved it further. And so they overshot their landing site by 100, 200 meters. And so they had picked a nice, safe landing site, but they ended up going past it. And when he realized that, he took control, went past the dangerous spot, and was lucky enough to find something they could land on at the last moment. So ESA's proposal actually put a kind of GPS around the moon. We don't need as many satellites, maybe 12 will do. They'll be in very irregular orbits, what they call litigious orbits, swinging out close to the moon and then further away again. The idea being that at any given time, any spacecraft or person or base will have 3 of them in sight. That'll allow you to navigate, you'll always know exactly where you are, and communicate. Again, infrastructure. You put a network up like that, then you don't have to carry as much radio equipment, you don't have to carry as much navigation equipment, you have additional things to work from so that you can be a little more efficient, save that weight, and get more done. And so the goal ultimately is to build a base on the moon. This is what Elon suggested. I think it looks like Burning Man, and probably not especially practical. It actually looks like Space 1999. Do you ever watch that show? It's like, it was a terrible English 2-season space science fiction. By the way, don't watch it, okay? And if you watched it as a kid, don't go back and watch it again. Your memories of that show are vastly superior to that show. You were a kid. I went and watched a few episodes. I'm like, I am ruining my childhood. I just turned it off. But yeah, base on the moon. Far more practical, this is what ESA suggested, was an airlock with an inflatable structure that you land on the moon, inflate, and then you use robots to bury it in a meter of regolith for radiation protection. It's not very sexy, but it's how people stay alive and have a place to be inside of the moon. One of the other proposals that's been flying around lately is to actually build a base inside of a skylight. A skylight is a collapsed volcanic tube. So we know, because our friend Jack told us and proved it, that there was volcanic activity on the moon back in the ancient times. And as those lava flows came up, they built large tubes that the lava flowed through, and when the pressure was relieved, a lot of that lava flowed back out and left behind a rigid tube. Some of them maybe a kilometer more across. And over time, when they were close enough to the surface, the tops of them collapsed. This is what they call the Marius skylight. And it's about 65 meters across the top of that opening and at least 80 meters deep. They believe the tube itself about almost 400 meters across. So it was one of these ideas that we could take an inflatable structure, put it down in there, slide it into the tube and inflate it, and now you have built-in radiation protection. The problem is that there aren't lava tubes on the poles where the resources are. All of the Apollo missions landed relatively close to the equator because of limitations of technology. And they all landed on the near side because they wanted to be able to communicate with Earth. So we've only actually been on very specific types of ground on the moon. We haven't explored the other areas. And so the skylight idea might be interesting later. Plus, in general, from a science fiction point of view, coming up from out of the moon with your rocket is cool. But I think initially we'll be building bases in the places where we can get the resources. Now, what are we going to do while we're up there? Well, we're going to use a lot of automation. This is actually a graphic from Caterpillar showing modified versions of the tractors designed to work on the moon. So building roadways, clearing spaces, burying objects, and looking for resources. So our goal is ultimately going to be able to survey, to look for resources, to mine them and refine them, and create products that we can use. So you can imagine a mining machine. This is actually a composite photo, a little bit of moonscape, but then they took a gravel processing machine. I just love the fact that they didn't take the telephone pole out. Like, that's the best right there. But yeah, find a bed of potentially useful minerals, and there's a lot of them up there. So the obvious ones are like silicon, iron, calcium. They're everywhere. But we also have concentrations of titanium, magnesium, phosphorus, aluminum, sulfur, some rare earths. In fact, it's really all of the ingredients if you wanted to make solar panels. Like, pretty plentiful. In lots of locations on the moon, we have everything we need to create solar panels. And solar panels are essentially growing crystals, which actually works better in lower gravity. There's a pretty strong case that the first product other than oxygen and water on the moon could be things like solar panels. We need them up there. In fact, there was a Japanese proposal to basically wrap the surface of the moon in solar panels. I don't know that it's particularly practical, but it's cool. But a far more useful thing would be to send them back to Earth. So you build these panels, you stack them up, you use a linear accelerator to accelerate a payload back off the moon. It's only 2 kilometers per second to get back off the moon, and you go back to geostationary orbit, where we start building space-based power. Now, space-based power is not a new idea. It's been around since the 1960s. As soon as we knew we could make solar power, and we also knew we could lift stuff into orbit, it's like, what if we put our solar power up there? Because if you're in geostationary orbit around the Earth, you don't have a night. You have sunshine all of the time. Now, it's great to have electricity up in orbit. How do you get it down to the Earth? Glad you asked. Let me freak you out. We're going to use a microwave rectenna about 1 kilometer across at the bottom of that thing, and we're going to beam microwaves onto the surface. It's the microwave. Now, that sounds crazy, but believe me, we already beam electricity around using microwaves today. It's a normal part of the power grid. It's not a lot of electricity, but it is some. 1 kilometer-wide rectenna beaming onto the Earth would land in an area about 10 kilometers across. Now, that concentration is not dense enough to, like, fry birds in flight, but you probably want to put a fence around it. And it is a gigawatt of electricity with no emissions. So when we talk about trying to decarbonize our power grid, this is pretty compelling, although normally, when you price this, it's insanely expensive. Lifting that much mass up to orbit to build a solar power station doesn't make any sense. But if you can lift all the heavy stuff, all those solar panels, from the moon, it does make sense. But more importantly, that little power plant doesn't just have to beam power onto the surface. I mean, it's very useful for that. Imagine in a disaster site where the infrastructure is smashed, the idea that you could just send in a crew, lay down an antenna array, this satellite steers and puts power there, and now you have immediate power available for the emergency workers. That's pretty useful. But you could also beam it onto a spacecraft. You know, every spacecraft needs some kind of propulsion system. A propulsion system is made up of a motor, a power source, and fuel. But you could make the power source external. You might not use microwaves, you might use lasers for this. But you could beam power to a vehicle. So you reduce the weight of the vehicle. If you look at spacecraft that use electric propulsion, so xenon thrusters, they typically have massive solar panels on them to get enough electricity together to actually be able to use that thruster. And even then, it's very low power. Imagine we need to move payloads back and forth between the moon, roughly 400,000 kilometers. So that's well in the range of a set of solar power satellites to have shuttles moving back and forth that they have to carry fuel and a motor, but they don't have to carry power plants. So we make a more efficient bus as we start working back and forth with the moon. Again, we're building up our infrastructure. So I've got bases on the moon, extracting resources. I have a relay system running back and forth the moon and the Earth. I have fuel state depots, both the moon and the Earth. And I have power generation. What's next? Well, now we can start looking at going after resources elsewhere in the solar system. So I can build a spacecraft that can actually go to those resources. There's a bunch of different kinds of asteroids of varying value and interest. The C-class are the most common type. This is the Mathilde asteroid, which we sent a spacecraft to explore. It's mostly water and some rock, carbonaceous rock. Has some nitrogen and potassium and phosphorus. So recognize that water is still our most valuable asset. It's very heavy to lift. You know, it's a kilogram for every liter of water. So any liter you can get from up there, the better off you are, and you need it all the time. So being able to extract water resources is enough. The other resources are also interesting. There are S-type asteroids. These are silica-rich asteroids. This is another picture of Didymos and Dimorphos. So full of silicates. We also know they're often rubble piles, which speaks to how easy they will be to extract from. You don't have to hammer the rocks apart. They're already apart. Just put them in some kind of processing. One last type to mention, there's actually a lot more types, but the big one here is what they call an M-type, or a metallic. These are nickel and iron, platinum class metals. We actually have a mission going to this particular asteroid. This is an artistic rendering of Psyche, which we believe might be an old planetary core that was ripped apart by Jupiter. And last year we sent a spacecraft to explore Psyche. It'll get there in 2029. There's been some new imagery taken by the James Webb of Psyche. That's very hard for the James Webb to do. And they're coming to the conclusion it's heavily oxidized. So it's not only an asteroid, it's a rusty asteroid. Now, how would you actually mine on an asteroid? Well, here's a vehicle called the Trans-Astra Honeybee, because it's sort of bee-like. So the asteroid goes in here. This is actually a known set of matured technologies for the asteroid redirect mission that never flew, but they did build a lot of the parts for how to envelop a small asteroid up to maybe 100 meters across in essentially a bag and enclose it. On the other end, these are solar collectors. So they collect sun, concentrate it to create a high energy beam to vaporize the rock. And then you use a gaseous extractor to collect that. Does it sound crazy? This part they've actually built. The optical mining bed is a real thing. That's the machine that can take a composite material like rock, vaporize it, and pull the different gases apart on it. So technologically, a bunch of these things need to be matured, but they're not outrageously complicated. So you take in an asteroid, you consume it, essentially vaporize it, sort out those respective vapors, combine them with chemicals to make them stable, tank them separately, and then ship the tanks off. You go to the asteroid, you dismantle it, and its component elements then are sent off for utilization. Now, you might send them back to the Earth. It's not particularly practical. You need a re-entry vehicle for that, and it tends to be expensive. The stuff that's on the Earth is cheaper, but we know that some resources are getting harder to come by, so eventually we'll start re-entering them. Mostly, you're going to want to use those products in orbit. Instead of lifting materials from the Earth to utilize them, you use them up in space. So now things get bigger. We've always had a limitation by building stuff on the Earth and having to fly it into space, that it has to fit inside a fairing. So it tends to have to fold up, stay lightweight. We make a lot of things out of aluminum because they're light. We can only lift so much. We don't need to do that if we build in space. So the more readily available elements like nickel and iron alloys, they're good construction materials. They're easy to work with. They're very durable. They're quite radiation resistant. And they're easy enough to build with. Yes, pure science fiction pictures. But one of the ideas you could take from that, once you're able to start building in space, is that you do build a space elevator. It's just that you build it on the moon. The lower gravity of the moon and the lack of atmosphere and the lack of radiation belts make it far more practical. You would build it on the far side of the moon. Why? Well, it's easier to get there by spacecraft than it is to do landing. So right away you get that advantage of a space elevator. But also, that point on the far side of the moon is a very energy efficient way to get everywhere else you want to go in the solar system. So after we've done the research bases on the pole and we're starting to do resource extraction, we construct a base on the far side of the moon on the equator. We build ourselves a space elevator, relatively short, doesn't have to be near as big, and that becomes a dock that you can construct things from. You can build resources from the moon, you can bring resources back from asteroids, start assembling larger vehicles and other equipment that we want to use. So let's get back to humans being in the equation on this. We do know from the International Space Station that humans have a tough time in free fall, right? Most of your body systems work just fine. Most of your body systems are peristaltic. They have pumps, your blood pumps, digestion pumps. Burping doesn't work. Although I've seen the demonstration on the space station of how you got to burp, which is that you got to back up to a wall and then accelerate off the wall so the food settles at the bottom of your stomach, and then you can burp. And if you get it wrong, you have to clean it up. But one of the systems that doesn't work on the moon is your cerebral spinal fluid. You have two organs inside your brain that produce a fluid that cleans your brain. And then it runs down into your spine where it does exchange with your kidneys to remove that detritus. For centuries, we've known that bedridden patients need to be sat up every day. It's only recently we've really understood that one of the reasons is so that spinal fluid does its thing. When you're in free fall, that fluid builds up in your head. It does not flow into your spine. And that's bad. One of the things is that there's so much fluid in your head it actually bends your eyes. You'll notice that every astronaut on the space station for any length of time is wearing glasses. In fact, they bring multiple pairs because their eyes change shape over the course of the 6 months that they're up there. You're always losing bone mass while you're up there. So they exercise 2.5 hours a day to minimize bone loss, but they lose it anyway. It's more than a year of rehab after 6 months on the space station before you can walk reliably and your bones aren't as embrittled. So imagine sending a set of astronauts to Mars, which takes 6 months in free fall. Then they get there. There's nobody to help them. Like, how would that even work? We need to build artificial gravity. Now, we don't have science fiction at our disposal, so we don't get to just turn it on. We have to build it, and it's going to be with rotating structures. And we know that humans like 1G best, and so we know we can build a structure that can rotate at different speeds, but it has to be large enough. If it's too small, you have a Coriolis effect. If it's a rotating structure that's small, the amount of gravity at your feet and the amount of gravity at your head are not the same, and that's a great way to throw up. So you have to get big. And if you got to be a G, the comfort zone here, you're getting up into the area of almost 100 meters across. We've never made anything that big. That's really very large. Now, we may not need a G. One of the things we'll learn when we have humans on the moon for an extended period of time is how well your systems work in 1/6 of a G. So we could get stronger there. But eventually we're going to have to build rotating structure spacecraft. If we want humans to stay healthy and be able to actually go to other places, that's what it's going to take. And we have to learn how to do that. Our new space stations will help with that. Our new construction techniques will allow it to be big enough. This is from The Martian. This is so pure science fiction, but actually its design is really very smart. It's well thought out. There's a big, like 60-meter rotating structure. Instead of making the whole thing a chamber, they put 4 chambers at the end. And then back here is nuclear propulsion, which is part of the equation. These are mostly heat radiators, actually. And then up here are the non-rotating structures, which does beg an interesting question. What happens when you have to perpetually go between free fall and gravity? Because the other thing that happens on the space station is for the first 3 days that you're in free fall, you're nauseated all of the time. Presumably, we'd eventually adapt to switching back and forth, but nobody knows. So another thing that we need to learn. The question is, where do you go? And of course, lots of folks, mostly eccentric billionaires, are talking about going to Mars. But it almost doesn't make sense. Like, well, you got all this trouble to get out of a gravity well. Why would you go back and get into a new one? And what's there? You can't breathe the air. In fact, don't breathe anything there. It's quite toxic. It's full of perchlorates. It has some gravity, but that's not really a feature. It has some resources, but they're not any easier to extract than you can from asteroids. So to get to the point where you can even go to Mars, we kind of don't even need to go. except maybe from the science perspective. But if you want to make places in space, with all the skills you've cultivated, the infrastructure you've built, and the way we can work in our solar system, why not just make your habitats? Take your rotating structure and get bigger. In the 1970s, Gerald O'Neill specified an idea called the O'Neill cylinder. We called them the L5 colonies. So think 8 kilometers in diameter for the central cylinder, 32 kilometers long, rotating very slowly to provide 1G. That bigger outer ring is the offset for the solar reflectors. It's also where you put all your factories. That some will need stronger gravity, some will need lighter gravity. It's cut up into 6 bands, so 6 land bands and 6 visibility bands, so that you have sunlight coming in that goes through filters so that it looks right and it's safe. And so that your inside world, sort of looks like this. That's room for a couple of million people to live. And if you want to go back into space, you take an elevator, go up to the central core, fly away. There's enough material in the solar system, just from asteroids alone, to build hundreds of thousands of these. We could be trillions of humans. They can stay around Earth orbit, but probably make smarter to move closer to Venusian orbit, more solar power, faster orbit times, lots of advantages for being down there. You've heard the concept in science fiction of a Dyson sphere. It's completely impractical. It almost certainly does not exist. But if you get enough of these together, you create a Dyson swarm, where you literally have habitats in multiple orbits. People get to live the way they want, in different systems, in different places. That's a spacefaring civilization. I think it's achievable. I hope I've outlined to you all of the pieces that we're already on the path to going there. This is not that much of a stretch from what we're already building today. Thanks so much for your time. I hope this is enjoyable. The .NET Rocks episodes out of the Geek Out, so you go to geekout.show, it'll take you there, and then you can type in space or nuclear or any of these. There's about 100 of them out of the 1,900 shows if you want to